Hey everybody, welcome to part 2 of chapter 4 notes. Start on 4.4 in the notes outline and we'll get going. Sorry it's like complications. Anyway, let's rock this stuff. Okay, first, oxidation reduction reactions encompass everything that we have left. Combustion, single displacement, synthesis, decomposition. They're all redox reactions. Oxidation occurs when an atom or ion loses electrons, and reduction occurs when an atom gains an electron. Oxidized, reduced. Oxidized, reduced. Let's watch a little film.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
That's so cool. All right, let's move on. Okay, just another chart. Here it's important to notice that the object that is oxidized, the one giving away those electrons, is called the reducing agent because it's causing this guy to be reduced when it gains those electrons. And the reduction chemical is called the oxidizing agent. Have fun with that. Oh, and in case you don't remember, there's a way to remember which is which. Two little acronyms. There's one called oil rig. Stands for oxidation is loss, reduction is gain. And then there's another one, if you don't like that one, Leo Gur. Leo the lion says Gur. Wish I could draw a line. Loss of electrons is oxidation, gain of electrons is, Gur, not Geo. All right, next. Okay, in order to do the understand how many electrons are being lost and gained, you need to know the oxidation numbers for each element. Those are the charges that we can assign to atoms, and it's easy to do with ions, but for molecules, there's some rules we have to follow. So let's go through the rules. First, elements in their elemental form, the way they would be if they're as they appear on the periodic table, have an oxidation number of 0. Copper, aluminum, any element in its elemental form has a 0 charge. Atomic ion, it's the same as its charge. So we've learned the alkali metals are all +1. So sodium, for instance, has a +1 ion charge. That is also what we would call its oxidation number. Cool. Huh? Okay, some more rules. Nonmetals tend to have negative oxidation numbers. Some are positive, for instance, lead, even though it's, well, that's a nonmetal. Take that back. Iodine can be a -1 or can be a +7 in some situations, depending on what it's bonding with. Oxygen, we can almost always count on that being a -2, unless it's in peroxide, such as hydrogen peroxide, and then it's a -1. But you would know from the name if it's a peroxide. Hydrogen can be +1 or -1. It's -1 when it's bonded to a metal, and +1 when it's bonded to a nonmetal. We typically see it as a nonmetal. Okay, more of those non-metal rules. Fluorine always has an oxidation number of -1. No options for fluorine. Other halogens are usually -1, but they can have positive oxidation numbers when they're bonded with oxygen or other more electronegative elements. The sum of the oxidation numbers of a neutral compound is 0. You've got H2O. The -2 for 0 has to be balanced out by 2 positive 1s for hydrogen. The sum of the oxidation numbers of polyatomic ion have to be the charge of the ion. So, for instance, the hydroxide ion, we can count on oxygen being -2, so the hydrogen must be +1, and that gives the overall charge of -1 for hydroxide that we expect. Now let's try it in a reaction. All right, so let's start with the elements. Aluminum is going to have a charge of 0 because it's in its solid elemental form, as does copper. Copper chloride is a compound, and those are ions. Chloride we can count on being -1. There's 2 of them, so total negative charge of -2. Copper must be +2 to make the compound neutral. And then over here, chlorine's -1, total of -3. Aluminum must be +3, and that makes that compound neutral. So far, so good, I hope. Okay, single displacement reactions are examples of redox because the ions oxidize some element. So in this particular reaction, it appears we've got magnesium metal probably in an acid. So the magnesium metal is going to give away electrons to probably the hydrogen in the acid, which then produces hydrogen gas and leaves magnesium ions in solution. So the magnesium was reduced. So you'd have magnesium plus HCl to give you magnesium ions after it has lost electrons, thus being oxidized, plus hydrogen gas by the hydrogen gaining electrons being reduced, because the hydrogen went from a +1 to a 0. Have to be 2 of them, obviously. And the magnesium went from a 0 to a +2. Okay. In this particular reaction, we've got silver ions oxidizing copper metals. Most of you saw this last year in the lab. So the silver was able to reduce and the copper was able to oxidize. But if you tried to put copper solution into a solution with silver metal, it would not go back that way. Why is this? This has to do with the activity series you see on the right side here. It's a series of experimentally derived relative activities. So at the top of these are what we would expect: the active alkaline metals, alkaline earth metals, and moving down to the transition metals, and even the heavy metals, silver, lead, mercury, gold. Hydrogen fits in down here, surprisingly not as easily oxidized as a lot of the other metals. So this series shows elements that are most likely to lose electrons on top and least likely on the bottom. And therefore you can decide what will replace what else. Something higher on the chart can replace something lower on the chart. Okay. Enough about that for now. We'll talk more in class if you have questions. About molarity, it's just a concentration review. Molarity is the most common way for us to measure concentration, and it's always moles of solute over volume of solution in liters. Really important. So if you're going to make solutions, which you will probably do for the lab tomorrow, you have to weigh out the known mass to a certain number of moles and dissolve it in a volumetric flask up to a known volume. Many of you did that last year as well. If you haven't, we'll be practicing that. Now, we often have to dilute rather than just make a solution from a solid, because many of our solutions, especially the acids, are bought in concentrated form, and sometimes we have a concentrated solution you want to dilute to a lower concentration. So you might use a pipette, put in a known amount, and dilute up to the line on a volumetric flask. This is figured out quantitatively by the following equation. The molarity of the concentrated solution times the volume of the concentrated solution, equals the molarity of the dilute solution times the volume of the dilute solution. So you can see that on this diagram. So everybody is pretty familiar with going from grams to moles, moles to moles, moles back to grams, but we can also do that with the molarity or volume of a solution by knowing the molarity and the volume. You can change it to moles, do the mole-to-mole ratio, and go back to volume. Pause and take notes on this if you think that would be useful. So let's do a problem. Try it all together. So let's say we have a solution of 100 milliliters of 0.200 molar potassium hydroxide and mix it with 200 milliliters of 0.150 molar nickel sulfate. So first, write a balanced equation for that reaction. Write that down. Okay, nickel plus hydroxide ion, nickel ions plus hydroxide ions makes precipitate, nickel hydroxide. Okay, what's the limiting reactant? We practice this for our quest. Take a moment. Figure out how many moles of the nickel ion, how many moles of the hydroxide ion you have to start with, and figure out what's going to run out first. Pause. Turn back on when you're ready. Okay, you should have found the potassium hydroxide is the limiting reactant. If you didn't, go back and try again. Remember, take the volume times the molarity to get the moles of each solution and then compare. And don't forget the fact that there's a molar ratio of 1 to 2 in the equation. Okay, next. How many grams of precipitate will form? So knowing the potassium hydroxide is the limiting reactant, you can now do some stoichiometry to find out the mass of nickel hydroxide. Pause. Okay, hopefully you got 0.927 grams of nickel hydroxide. Finally, what's the concentration of each ion that remains? So think through that a little bit. You started with a certain number of moles of nickel, of sulfate, of potassium, of hydroxide. What has been completely used up? What can we say is gone? Okay. You said the hydroxide, you're right. The hydroxide will be completely gone because all of it and the limiting reactant went into the nickel hydroxide. What about the potassium? Now the potassium should all still remain. You have a certain number of moles of potassium ions but now you've got a new volume. So your potassium ions need to be, moles of potassium ions need to be divided by the total volume, 300 milliliters. That'll give you a start. See if you can figure it out, and then check your answer. 0.0667 molar nickel, 0.0667 molar potassium, and 0.100 molar sulfate. Notice all the hydroxide is gone. All right, finally we're going to do a virtual titration in this unit, and we'll do many more later. But for now, we're going to try the analytical technique in which one can calculate the concentration of a solute in a solution by comparing to a known concentration. We will use a phenolphthalein precipitate or acid-base indicator, which will turn pink just when it turns basic. And we'll do some practice problems in class. I think that's enough for tonight, folks. We'll see you soon. Good night.